They say that by looking at our past, we can predict our future. Well, here's a crystal ball from our past. This is, as you can see, a carburetor. But more importantly, it is also a bad idea. It is a bad idea because with this particular design, Yamaha, or more precisely a Japanese carburetor and fuel and intake systems company called Teikei, tried to make this carburetor do something that a carburetor cannot do. And that is to behave like a small and a big carburetor at the same time. Sort of like what we're doing with small 1-liter 3-cylinder engines nowadays, that we are trying to give them the performance of much larger engines, while at the same time somehow trying to maintain the fuel economy and emissions of a 1-liter 3-cylinder engine. History teaches us that two-stage carburetor designs like this one were quickly replaced by simpler carburetors and or fuel injection. They sounded great on paper, but in the real world, they offered no benefits and they were very hard to tune. But you see, there's a problem. This particular carburetor comes from my Yamaha TT600R, a motorcycle that I have a very deep and complex emotional and sentimental connection with. It is a kickstart only motorcycle that is also cursed. I've been working on it for the past 10 months, but I can't get it to start easily and run right. And I'm this close to getting rid of it and just buying something slightly used, newer, or completely new with electric start and, just ending this nightmare. But I really like the bike and I just can't give up on it. And so I keep giving it one more chance and one more chance and one more chance. I've replaced pretty much all the electrical components. I replaced the rotor. I even turned the capacitor into a lithium battery to improve things. And I replaced a bunch of other parts. I got 2 aftermarket ignition boxes, you name it. And I have improved things, but it still doesn't start easily and it doesn't run the way it should. And now I'm 100% sure that this is the final boss, this is the culprit, because I cannot tune this carburetor to function the way a carburetor should. And I'm not a carb tuning guru, but I'm also definitely not a beginner. I got a car engine to run on motorcycle carbs, and I have done numerous carburetor rebuilds and tunes, both on 2-stroke and 4-stroke bikes, but this one, no. And here's why. To get the bike to start, sometimes this wants 2.5 turns out on the pilot screw, the fuel screw, which is right here. With that setting, it starts sometimes. And when you start it and get the bike to, warm up, you ride around. And then if you turn the fuel screw out 3 turns, you are going to feel a very noticeable improvement in power and responsiveness from a low RPM. The bike feels more alive. It is telling you that is the right setting of the pilot screw, and the factory service manual also agrees with you. But when you finish your ride with 3 turns out, you come back home, you turn off the bike, and then you want to ride it in a few days, it will not start with that setting of 3 turns out. It will kick back most of the time, which is very annoying and kind of painful, and it also scares you. Or it will sputter, or it will sort of start for a millisecond, and then just die. It will do everything except starting. And then you have to put it back to 2.5 turns out, which is not easy. You have to get under there in the carb. It's all a big pain. And I have tried everything. When I say everything, I mean everything. I have tried every possible setting of the choke, every possible setting of this idle speed setting. I have tried priming the engine, a bit of throttle, more throttle, less throttle. A lot of throttle gives you a lot of kickback. I have tried new fuel, old fuel. I have tried different pilot jets. I have tried air filter on, off. you name it, even silly things like indexing the spark plug, increasing the spark plug gap to be larger than factory recommended. None of it works. It will not start. But here's the final nail in the coffin of this stupid design. And it is that even if you get it to start easily and run right and somehow you manage to tune it magically to be perfect, this thing is a two-stage carburetor. So at idle, low, and sort of medium throttle, only this carburetor works. It is only this one that supplies the fuel to only one of the intake ports of the engine. As you increase the throttle and somewhere beyond, I think, half throttle and RPM, this other constant velocity carb, this lifts up, and it joins in and starts providing fuel to the other intake port of the engine. Which means that because the intake ports on this engine are physically completely separated, one of the intake ports is beautifully clean, whereas the other one is nasty and dirty because the other carb, of course, doesn't run all the time because a lot of the times it's a 600cc single, you're doing just a bit of throttle. So even if you tune this perfectly, you will not get rid of this inherent sort of annoying feature of this and all other two-stage carburetor designs. It's not detrimental to the engine longevity or performance or whatever, but somehow it is just annoying. And so I decided to install a completely different carburetor onto my Yamaha because that was the only problem that it still had. It wasn't the fact that it's a 26-year-old piece of garbage, it's the carburetor. So I decided to replace it, but there was an obstacle to me installing a completely different carb, and that's that the Yamaha TT600R was never a global nor a very popular model. So the aftermarket for it is pretty much pathetic. Yamaha themselves, the only things they still make for this bike is, I believe, some of the bolts, some of the gaskets, and the oil filter. That's it. Basically, nobody really cares about this bike anymore. The only thing I found in terms of carb conversion kits was this from Australia. Even with the very favorable exchange rate, it is still pretty expensive and it requires me to grind away parts of my frame and my engine to fit it. I wasn't ready to do that, and so objectivity and sanity were telling me to not undertake this project, but objectivity and sanity, they're not so fun. So I decided to dig deeper, and soon I found out that all the motorcycles that can be considered successors to my Yamaha TT600R, they all have fuel injection. All the predecessors use pretty much the same carb. So I had to look elsewhere for a suitable carb candidate, and I did find it in the end, but it took a bit of creativity. It took the addition of 2 more wheels. It took this. The Yamaha Raptor 660. It has 60 more cc, but it also has a beautiful and most importantly conventional Mikuni BSR 33 carburetor. So these 4 diameters are the same in both carbs, and the distance between the bores is also the same, which means that all I needed to do was some very mild mutilation of the stock intake boots to get the new carbs to beautifully fit onto my bike. Another good thing is that you can find dirt cheap Raptor 660 knockoff carbs on Amazon, which allows you to experiment inexpensively, which is exactly what I did. Of course, when you try to do silly conversions like this one, nothing is straightforward. For example, the throttle cable tube was sort of hitting my cylinder head, so I had to make a totally different one using a hose fitting. The stock fuel petcock also didn't clear the new carburetor, so I had to get a different fuel petcock, but then the stock choke didn't clear the new fuel petcock, so I had to get a different choke cable, which had a curve in it to clear the new petcock. Surprisingly, the choke from a Harley Davidson fits perfectly. All of these were problems, but they were easy enough to solve. What followed was a problem that was not easy to solve. These are the stock intake hoses which connect the stock airbox to the carburetor. With the new carburetor in place, they were now too short offset, and one of them had a completely wrong diameter, which means there was no way to connect the new carb to the airbox. I didn't know what to do, so I googled around, and to my surprise, I found a few more people online doing this exact conversion: Raptor 660 carbs onto a Yamaha TT or XT600 motorcycle. But the solution that I found from them was to simply completely eliminate the stock airbox and then just install tube or pod filters or whatever you want to call them. This might be fine for a street-only motorcycle, but I ride this bike pretty much exclusively off-road. And off-road, there's a lot of dust and a lot of dirt, and pod filters, they simply don't filter as well as off-road oiled filters, especially when they're completely exposed to the elements, so engine longevity might be negatively impacted. Also, pod filters, when they're off-road like this, exposed, they get very dirty very quickly, so you would have to change them all the time. And if you ever drop your bike while doing a water crossing, they get completely soaked with water, and water probably comes into the engine, and then starting or kick-starting your bike again is pretty much impossible. And so in my case, the airbox had to stay. It's simply the best solution for an off-road motorcycle. And to adapt the new carburetor to the airbox, I decided to undertake a pretty ambitious DIY adventure to do something that I have never done before, and that is to design and make from scratch a completely custom rubber flexible intake hose, aka intake duct. As you can see, in the end, I did it, but it was not straightforward. But I did learn many valuable and useful DIY lessons, all of which I'm going to share with you in this video so that you too can make completely custom intake hoses and ducts so that you can adapt pretty much any carb or throttle body to any engine, so that you can make completely custom intercooler hoses, turbo hoses, other intake stuff, coolant hoses, you name it. You can do all of it yourself. Before I even started the project, I decided that I was going to 3D print the new intake ducts in my Bambu Lab H2D printer using Bambu Lab TPU filament. TPU being thermoplastic polyurethane. I decided this because in the past I had already printed successfully some simple TPU parts, some gaskets, and so I decided that, hey, an entire intake duct shouldn't be much harder. But before I could 3D print anything, I needed a 3D file. I needed a CAD file of what I was going to print. And I needed to draw something similar to the stock pipes, but a bit longer and offset a bit differently with a different diameter on one of the pipes. And the problem there is that these are extremely complicated parts, way more complicated than anything I have ever drawn before, because for starters, for example, here's in the airbox, as you can see, there's a little notch, and that notch corresponds to a little tab or protrusion on the pipe right here that locks the rotation of these pipes in the airbox. The two pipes are different because they're mounted in different heights on the airbox. They have different offsets. They have some flat parts, some curved parts, and they are irregular and offset in pretty much every plane. And so to get this to fit, I have to get every dimension absolutely correct, because everything has to correctly reference everything in all the 3 dimensions for this to fit even closely. And I know what you're thinking. Hey, get a 3D scanner. This is the perfect candidate for 3D scanning. And yes, it is. It is black. It's not shiny. It's complicated. But 3D scanners are not cheap. And I was not going to get one just for the sake of this one project. Yes, I know people do 3D scanning with their phones. But I have an ancient, cheap, horrible Android phone with a horrible camera. And I was not going to upgrade for the sake of this one project. And I was confident that it can be done more simply. So I went full old school and just measured everything by hand using a caliper and trying to get as many dimensions as humanly possible. After that, I opened up Onshape, I drew a spline based on the dimensions I took, and then I did a sweep along that spline, and then I shelled out the resulting part to create my intake pipe. As you may already know, Onshape has become my #1 go-to 3D CAD software because it's 100% browser-based. And that means that your PC hardware becomes irrelevant, your work never crashes, it's always automatically saved, there are no annoying updates, you can access all of your work from anywhere in the world on any device at any time. They have an amazing public library of all kinds of files for you to experiment with and learn, and they have an amazing library of videos and tutorials to get you started in case you're new to CAD. If you want to try it yourself, links are in the description. Once I had my drawing, I opened it up in Bamboo Studio and printed it. I used the automatic TPU printing settings, which the system selects for you when you choose the Bamboo Lab TPU filament, and the pipe came out absolutely perfectly on the first try. And here it is, a fully 3D printed intake duct. It looks amazing, but I'd be lying if I said that I was surprised by how well it came out on the first try, because to be honest, I'm kinda used to things working perfectly on the first try with my Bamboo Lab H2D. However, what did surprise me was just how insanely strong this thing is. You can stab it with a screwdriver. You can try to twist it and tear it apart. You can do whatever you want with it, but it will stay intact. It is just as strong as the factory rubber part. The strength caught me off guard to the point that I wanted to find its limits. So I quickly drew up a super simple container to test the maximal internal pressure something like this can take. After the H2D printed past this hole, I hit pause. I then moved the bed down and inserted a tube valve through the hole. And then I let the printer resume. My Bamboo Lab H2D automatically references everything, so once I hit pause and resume, I can do whatever I want in the meantime, but it remembers exactly where it stopped and where it needs to continue. So the only thing I have to do is hit pause and resume. And this of course means that you can get very creative and insert all kinds of things into all kinds of holes and slots and then continue printing, and they're going to remain trapped or fixed in their hole or slot. This opens quite a few very interesting DIY possibilities. Once the part was done, I let it settle and stabilize overnight, and then tomorrow I tried to inflate it to a pressure of 150 psi, which is approximately 10 bar.
I can't believe it inflated to 150. I really hope the valve stem is leaking or something, because I do not want to go there now. No, it's holding 150. This is insane. Okay, this is version 2.0, which I did make a bit thicker because the previous version, the one that you saw printed, that was thinner, 1.5 millimeter wall thickness. This is 3.5 millimeter wall thickness, because that helps the valve stem seal a bit better. My whole method of valve stem insertion isn't the best. But honestly, I still can't believe it's holding 150 psi or that it survived that for any amount of time. That's insane. Wow. But I really hope it's leaking, because otherwise I don't want to go near that thing. Yeah. Definitely a stupid idea.
Another test I did in parallel is that I dunked my old TPU seals inside gasoline and diesel and let them sit for 3 days. They remained perfectly intact and completely unaffected by either one of the fuels. They didn't swell or become weak or brittle or anything else. So it's super strong, it resists both gasoline and diesel, it can take high internal pressures, it's already well known that TPU can take coolant without any issues, and it has a melting temperature of 183 degrees Celsius, which means that this thing is right at home on a motorcycle or a car, right at home in the engine bay. You can make any kind of duct, hose, you name it. Back when I was doing my Project Underdog Turbo 4AFE Toyota MR2 Mark I, I didn't have a 3D printer, but honestly, if I had, it would have made things so much easier, because what I was doing the whole time, what we were doing is to fabricate little metal brackets and things so that we can position things to fit the only kind of hoses that you can find in the aftermarket, which is you have straight or 45-degree bend or 90-degree bend, and that's it. And you have to work around that, but not with this. But printing TPU is a bit different. It's not harder, just a bit different to printing your classic plastic type filaments. And in order to achieve these kind of results that I have achieved here, there are some very important things that must be observed. Number one, you have to dry the filament beforehand. This is a must. It is non-optional. I recommend drying 16 or even 24 hours. I use the AMS HT, HT being high temperature. I love it because it fits perfectly into the Bamboo Lab ecosystem. You just load the filament, you choose what kind of filament you want to dry, and then it automatically selects the temperature and the drying time, and then you can choose whether you want to rotate the spool or not, and that's it, you're done. But the best thing about it for me is that you can start new drying cycles using just your phone. You can load the filament, and then you don't have to be at home when one drying cycle finishes and you want to start another one. You just access the AMS HD through the Bamboo Handy app and just start another drying cycle. This is incredibly convenient. I used it hundreds of times already, because often I like to do 2 or even 3 drying cycles, and when one ends, I'm often not at home, and this makes it super convenient. The other very important thing once you're done with the drying is how you load the filament into your printer. I highly recommend to get rid of all PTFE, tubing, hoses, whatever you want to call them. Load it manually directly into the extruder. This way the TPU filament will never get stuck. You will never have a failed print because of stuck filament. Now, a pro tip here is to keep the filament inside the AMS HD while you're printing. Load it manually through the little convenient hole in the lid of the AMS HD and then into the extruder, and then you set another drying cycle while it's printing, only without rotation this time, so that the extruder can easily pull the filament. This prevents the filament from absorbing moisture during the print, and it ensures perfectly consistent quality across the entire part, which is the secret sauce to ultimate strength. The other two important bits are to use a 0.8 high flow nozzle. That's what I used, and this thing is worth its weight in gold because prints that lasted like a few hours are now 20 to 30 minutes, and the thick big extrusions, they make the part stronger. And finally, while printing, remove the lid of the printer and keep the door totally open because TPU is extruded hot, but it needs to cool down as fast as possible for ultimate strength and performance. When it comes to the printing settings in Bamboo Studio, make sure to increase the number of walls to some silly number like 20 or 30 to ensure that the part is solid TPU without any infill, which leads to ultimate strength. All the other settings I leave as is, and they are automatically pre-selected by the software when you choose the TPU filament. The only thing I have changed is the top and bottom Z distance. I increased this to 0.3. This makes support removal easier while still retaining perfect strength. I have used same material support for convenience and simplicity. I'd also like to point out just how cost-effective this is, because I printed out all of these gaskets and seals and all of these intake tubes plus 2 more that are on the bike from just one roll of Bamboo Lab TPU, and I still have around 40% of it left. And the size of the Bamboo Lab H2D means that you can print much larger parts than the ones I did. So I had made a part which was super strong, very resilient, also very pretty, and also a total failure. It was a failure because my dimensions were totally off, as much as 5 or even 10 millimeters in some places. The only thing I got right were the diameters, these two at the ends, nothing else. I just couldn't fit this properly. And this idea to use this hose takeoff and then attach or glue a regular hose from the parts store and then connect that to the diaphragm breathers on the carb, that didn't work either because I overestimated the amount of space available within the confines of the frame. There's not a lot of space at all. This didn't work. This thing just didn't fit. So I set it aside, went back to measuring, tweaking, drawing again, and I made version 2.0. As you can see now, the diaphragm breathers are integrated into the tube, so there's enough space. I can just, push them onto the carb, but this was also a failure. I got the angle of one of these right, the other one I got wrong in reference to the center of the main carb diameter. I got other things wrong that were somehow previously right before. This didn't fit either. And then I realized that trying to get it to fit, trying to get dimensions right like this by measuring by hand with the caliper and essentially it boils down to eyeballing things, it was never going to work. So then I got to thinking and I tried to be creative, and eventually I came up with a sort of very simple and kind of primitive approach that was also kind of genius. What I did is that I took a perfectly frontal, straight photo of the stock intake hose. I then imported the photo into Onshape and resized it to match a known correct dimension. After that, I just drew circles along the path of the hose photo, and I just lofted all the circles together and then shelled out the part in order to obtain my final hose shape. I did the same trick with the carburetor. I took a perfectly frontal photo and then resized the image in Onshape until the diameter of the intake matched. I was now able to measure the angle between the center of the carb and the diaphragm breather with perfect accuracy, which meant that I could accurately implement it onto my hose as well. I printed the new hoses out and voila, they fit perfectly. There you go, 0% 3D scanning, 100% accuracy. All it took was the right software features and a bit of creativity. Once I had the hoses ready, it was time to install them and put the bike back together. And once the bike was assembled and the moment of truth came, I couldn't try to start the bike. You see, this motorcycle kicked back so many times in the past.
Oosh.
That I think it probably traumatized me or something. I didn't try to kickstart it in a month, and it seems that during that month, somewhere in my subconsciousness, a very strong reflex or fear had formed, and I just couldn't start the bike. It was a very weird, very strange experience. Never happened to me before, but I just couldn't not try to start it. So what I did is that I pushed it up the slope in front of my garage and then tried to just push start it, and to my great surprise, it started on the very first try. This never happened with the original carbs with 3 turns out on the fuel screw. It would never push start. I tried many times. The bike would just clatter or make some weird noises or lock up the rear tire and just slide across the garage. But now it started on the first try, and to my great surprise, the Amazon carb seemed to have pretty good fueling out of the box. I think it still needs more tuning because it kind of stumbles a bit when you take off, but other than that, it seems okay, and I'm pretty sure that now the tuning process is going to be a lot more straightforward than with that 2-stage carburetor monstrosity I had before. So there you have it. I did what I wanted to do. But what's more important than that is where my little story fits in the bigger picture. Some 20 years ago, it was impossible to imagine 3D printing, widespread 3D printing at the consumer level. 10 years ago, printing complex and strong TPU shapes at the consumer level was extremely difficult, if not impossible, and it was also very cumbersome. Today, as you can see, it's not. And I hope that in the future, 3D printing goes even further and achieves more things and gives us even more doors and more options just like this. I hope that, for example, in the future, metal 3D printing at a consumer level becomes viable. And if all this happened, I have high hopes that that will happen too. The rational modern approach would be to just get rid of this motorcycle and buy something, modern, more efficient, whatever. But I want this bike. I like this bike. I like its analog, brutally simple mechanical nature. I like the fact that I don't have to turn off ABS and traction control every time I start the bike because this bike doesn't have any of those electronics. I like the fact that it has a needle instead of a LCD. I like all of that. I'm not saying that modern bikes are bad. I might buy one sooner or later. It's great to have that too. But I also want to have the freedom and the ability to keep this bike, to have it and to improve it and to keep it alive without having to be at the mercy of the aftermarket or Yamaha. And that's what 3D printing is allowing me right now. I have a bunch of other 3D printed stuff on this bike. For example, I made an adapter for the front mudguard. I broke the original one. None of the aftermarket ones fit. Original ones are insanely expensive and rare. And then I just made a little weird adapter to fit whatever I wanted. It's little things like that that really help. And something else that really helps is the beautifully smooth user experience of Bamboo Lab stuff. It just works out of the box without hassle and troubleshooting and whatever. What I also want to say is that nowadays we live in a market, in a reality where OEMs are trying to make it impossible, or at least as hard as possible, to modify the products we buy and own. They are trying to lock us out of the products. The aftermarket also favors popular platforms, which of course leads to, the highest sales. It's understandable. But personal manufacturing is the only way that we can fight back against a market of limited options, locked products, subscriptions, and just the overall trend of enshittification, as it's called nowadays. Personal manufacturing opens the doors to a freedom that I think every DIY enthusiast dreams of. And nowadays, a bit of investment in some CAD skills and a 3D printer can open hundreds of doors. In the future, I really hope that it will be thousands upon thousands of doors until we eventually open all of them and have complete freedom of personal manufacturing, which I think over time will also force the OEMs and the aftermarket to treat things differently and to offer more value and less locking and compromise. So that's pretty much it. As always, thanks a lot for watching, and I'll be seeing you soon with more fun and useful stuff on the D4A channel.